Good afternoon, welcome. I'm excited to open this four-session course hosted by LISER and co-organized with the University of Luxembourg, the Doctoral School in Economics and Finance. We are honored to have Professor Clément de Chaisemartin leading this course on difference and differences for us. He needs a little introduction. You all know his work that has been reshaping the field of causal inference, especially in the ever-expanding area of Diff-in-diff. I will not waste too much time on anything else because we have already wasted too much. So just remember the class is supposed to be recorded. I hope it's working. Then it will be shared on LISER's website and social media channel. For questions, feel free to write in the common chat. We are going to forward the questions to Professor Chaisemartin by ourselves, so just write on the common chat. We are many people, so we will not probably have time to answer to all of them, but we are going to select the most important ones. Please put mute everybody. Thank you. Verify that. That's it from now, from me. For now, again, I'm thrilled to have Professor de Chaisemartin here, and the floor is yours, Clément. If you want to start, I hope you have all the rights to start the presentation.
Perfect. So thanks everyone for coming. Now everyone sees my screen correct with the lecture notes. So just a few words of introduction about this class. So we're going to be following this textbook that Xavier and I are writing, and titled Credible Answers to Hard Questions, Diff-in-diff for Natural Experiments. So I sent you the latest version of the book. It's finished yet, but parts of it are finished. We've tried to divide the book into more and less important material. So the slightly less important material will be indicated with an asterisk side. We would not go over it during the class. As you will also see, the lecture notes include many questions highlighted in blue and in green. So the questions in blue are more like conceptual questions to try to make sense of the mathematical notation and results that we're going to be reviewing together. And whenever we encounter one, I will give you a little bit of time to think about the question and then see if some of you can come up with an answer. And then there are the green questions, which are more applied questions when we're going to try to implement code in Stata on real data sets to illustrate the concepts and the estimators and the new commands that we're going to be reviewing together. And I saw in the chat of the other session that many of you have already downloaded some of the data sets that we're going to be using. Okay, so that was it for the introduction. So I'm going to directly jump to the book's second chapter about the conceptual framework. So which type of data are we going to be using? What's going to be the notation we're going to be using? And what are going to be the main assumptions we're going to be making about our data? So the goal is to conduct causal inference to estimate the effect of a treatment variable, which is going to be denoted D, on an outcome variable that will be denoted Y. And we're going to be interested in cases where we're using panel data to answer this type of causal question. And we're going to be focusing on a slightly specific case of panel data, which can be group-level panel data. So we're going to assume that we have big G groups that are observed at T periods. And typically, groups are going to be locations like states or counties or municipalities or regions. But a group could, of course, also just be a single individual or a firm. But because most DID applications, Diff-in-diff applications, actually use aggregate panel data not at an individual or at a firm level, but at the regional level or at the municipality level. We think it's helpful to highlight from the get-go the fact that the application we have in mind do not only cover individual level panel data, but also aggregated panel data. And so the way this group level, this GT level panel data is constructed is not going really to matter for the class. There are many ways that you could come up with such a data set. For instance, you could have a repeated cross-section data set, a repeated survey of individuals, which for each yearly wave, you're going to aggregate individuals' answers at the municipality and year level. That's the way you're going to be constructing your municipality and year level panel data. We could also have a single cross-section data set where we aggregate the data at the, let's say, county of birth and the year of birth. And that's this year of birth variable that's going to be playing the role of or time variability in all of that. Okay. So irrespective of how this data set has been constructed, we're going to assume that we have a GT level panel data set. And we're going to be considering estimators that are not going to be weighted by by the population LGT of a cell GT. And we are also going to assume that the group level panel data set is balanced, meaning that the outcome and the treatment of each group is observed at every time period. This is mostly to reduce the complexity of our notation. And I don't think we're going to be covering that material together, but you can look at the sections of the book listed there to see how all of what we're going to discuss can be extended to imbalanced panels or to situations where you would want to weight your estimators by the population of cell GT. So, DGT is going to denote the treatment of group G at T, and board DG is going to be a vector that's stacking the treatments of group G from period 1 to period T. And then we're going to have a board D that's going to stack together the treatments of all groups at every time period. And we're going to refer to board D as the design of a study. So now that we've defined the treatments, we can define potential outcomes. So we're going to be trying to do causal inference. And so trying to do causal inference requires introducing a potential outcome notation. At this stage, we're going to consider an extremely general potential outcome model, which we will immediately start restricting. But for now, I'm assuming that the outcome of group G at time T can depend on the entire sequence of treatments of group G, but also on the entire sequence of treatments of all other groups. Okay, so at this stage, we can have that my future treatments affect my outcome, my past treatments affect my outcome, but also the past and the future treatments of other municipalities affect my outcome. And then YGT is just the actual outcome given the actual realization of everyone's treatments. Okay. So the main assumptions we're going to be considering are going to be of two different kinds. First, we're going to be considering exclusion restrictions, where we assume that actually, in this very, very general potential outcome model here, where the outcome of G at T is allowed to depend on capital G times capital T arguments, namely the big T treatments of all the big G groups, we are actually going to assume that some of the arguments in that function do not matter, and that the function does not depend on some of the arguments. So the first arguments we're going to be excluding from the potential outcome function in most of this class are others treatments. Okay, we're going to assume that the outcome of municipality G only depends on the treatments of municipality G and not on the treatments of other municipalities, which is often called a no spillover or stable unit treatment value assumption SUDVA, okay, which is stated here. My outcome only depends on my own treatments, on the outcome of G only depends on the treatment of small g, not on the treatments of unit 1, of group 1, group 2, and group B. So, of course, this assumption is quite strong. It could fail if you have, for instance, spatial spillovers where, let's say, for instance, that a municipality is going to change its minimum wage, while workers from other municipalities could actually work in that municipality that's changed its minimum wage, and therefore that could also affect workers in different municipalities, workers from nearby locations. Okay. So we're still going to maintain this assumption for a not very good reason, which is that very few papers have actually attempted to relax the assumption in Diff-in-diff designs, even though very recently that's a topic that has started to receive a bit more attention. And we won't review that structure together much, but there are subsections of the note that you can look at that explain you the few approaches that are out there to deal with spillover effects in Diff-in-diff estimation. So then another type of exclusion restriction we're going to be making is that we've already excluded everyone else's treatments from the potential outcome function. Now we are also going to assume that the potential outcome of group G at time t does not depend on their future treatments. Okay? Does not depend on their treatment at t+1, t+2, etc., which is called a no anticipation assumption. And so this assumption is plausible when the introduction of the treatment is hard to anticipate, but it's less plausible when the treatment is announced, the introduction of the treatment is announced very saliently ahead of time. Then there is an easy fix, actually, to potential violations of this assumption, which is just to redefine the treatment, to redefine a GT cell as being treated if at period T, it has already been announced that group G will get treated in the future. So in cases where there is a very clear date when the treatment was announced, and prior to that date, nobody could know that treatment was coming up, then there is a very easy way to ensure robustness to the violations of the anticipations. Again, we will see also how this type of assumption can be tested. Okay, and finally, a last exclusion restriction that we will sometimes make, even though most of our results will not require making that assumption, but sometimes we will consider that assumption. So that's an assumption that actually the outcome of group G at time t does not depend on the lagged treatments, does not depend on past treatments, but only depends on the current treatment. Okay, and that leads to a potential outcome notation of YGT just of DT, the current treatment, and nothing else affects the potential. And if actually the treatment is binary and you make this no anticipation and no dynamic effects and A and D assumptions, then each cell GT has only two potential outcomes. YGT of 0 is if the cell is untreated, and YGT of 1 if the cell is treated. And then we're back to the standard Robin model of potential outcomes with the Y0 and the Y1 that many of you are probably already familiar with. This simple model of potential outcomes is not going to be our baseline model like in this class. Instead, our baseline model will be this model here, where we assume that the outcome of cell G at T can depend on its current treatments dt, but also on the lag at tt minus 1, on tt minus 2, etc., all the way to t1. And this model was actually introduced by Robbins in 1986. Okay, so those are the exclusion restriction type assumptions that we're going to be making. The second key assumption we are going to be making, and that many of you are probably already familiar with, is the so-called parallel trends assumption. We're going to assume that groups are on parallel trends. And so we're going to introduce many different types, actually, of parallel trends assumption in the class, but the baseline one is expressed here. So first, I'm going to denote by ball 0 t a vector of t zeros. And so with this notation, YGT of ball 0 t is the potential outcome of group G at time t in the counterfactual state of the world, where their treatments from period 1 to t are all equal to 0. Okay? So I'm going to call this potential outcome YGT of ball 0 t. I'm going to call that the never treated outcome of group G at t. The outcome of group G at t if group G is never treated from period 1 to t. And so our parallel trend assumption is going to be a parallel trend on the never treated outcome. We are going to assume that for every t greater than 2, the evolution of the never treated outcome of group G between period t minus 1 and period t is in expectation the same for every group. Okay? So what this assumption says is that in expectation, if groups had never been treated, their outcome evolution would have been the same over the entire study period. Okay. And so we will discuss actually together some potential relaxations of this parallel trend PT assumption. So actually, I'm going to highlight right away the connection between parallel trend assumption and two-way fixed effects model. Turns out that this PT assumption here is equivalent. There is an if and only if relationship between the PT assumption and assuming that the never treated outcome follows a two-way fixed effect model. So to see that, we can start by noting that this long difference here, where we look at the evolution of the never treated outcome of group G from period 1 to t, well, using telescopic summation, where you can, for instance, always write the long difference from period 1 to 3 as the sum of the first differences from period 1 to 2 and from period 2 to 3. And that's what I'm using here, except that instead of 3, I have an arbitrary t. Now, each under this PT assumption here, each of those expected first differences are constant across G, are constant across G, are the same for every group. Because each element in the summation is constant across groups, then the summation itself also is constant across groups, and therefore I'm going to let gamma t denote this quantity here. And you see that my gamma is indexed by t, but not by g, to highlight the fact that this quantity does not depend on g. Then I'm going to let alpha g denote the outcome of group G without treatment at period 1. And then I can always say that the outcome of group G at time t without treatment under the counterfactual of never being treated is just the sum of its period 1 outcome without treatment plus the evolution of its outcome without treatment. I've just added and subtracted and this quantity here, so I've not changed anything. And now using my notation, I can write this as gamma t, and this is an alpha g. And this gives me a decomposition of the expected untreated outcome into a two y-axis effects model that's additively separable into something that's group specific and something that's time specific. And there is actually a leap and unleap, because if this assumption holds, if we have a two-way model for the untreated outcome, then it's easy to verify that this assumption here is going to be satisfied. Okay, and finally, I can let epsilon gt be the difference between the realized untreated outcome of group G at t minus its expected untreated outcome. And then I have that my realized outcome is equal to my expected outcome plus the difference between my realized and expected outcome. And so I have that the untreated outcome is the expected plus the error epsilon gt. And because my expected outcome can be decomposed following the two-way model, I get that my realized outcome is equal to a group fixed effect, a time fixed effect, and this error that's whose mean is equal to 0 based on its definition. So the parallel trends assumption that I've been imposing at this stage is a little bit strong, because it assumes that all groups are experiencing the exact same trends. It turns out that for most of the results that we will see together, they hold actually under a weaker assumption, which is that the treated and the control groups need to experience on average the same trends. Okay, so for instance, if we have a simple design where we have a binary treatment and G1 group are treated and the treated group are denoted as DG is equal to 1, and we have G0 control groups denoted by DG is equal to 0, most of our results are going to hold if in expectation the average outcome evolution without treatment of the treated groups is the same as the average outcome with evolution without treatment of the control. Okay, so we don't necessarily need to assume that all groups are experiencing the same trends. For many of our results, it's going to be enough to assume that on average, the counterfactual trends of the treated and the control groups are the same. Okay, and we're going to see in details soon that a nice feature of the no-anticipation and parallel trend assumption is that they are partly testable. And to test that, we will be checking that on average, treated and control groups are following parallel outcome evolutions before the treated get treated, which is called a pre-trends test. Okay, so at the risk of embarking in slightly philosophical discussions, I still think it's a little bit useful to clarify what's the framework for statistical inference that we have in mind in this. Okay, so when you are interested in doing causal inference, the reason why you want to do statistical inference, the reason why you want to construct confidence intervals, statistical tests, etc., is to assess if your estimator of the treatment effect really reflects the effect of the treatment, or could just be an artifact of chance, created by chance, created by randomness. And therefore, if we want to draw inference, then we have to introduce a source of randomness in our model. And there are typically three ways of doing that in causal inference. So the first way is to take a design-based perspective where we assume that the potential outcomes are fixed or they're conditioned upon. And what's random is the treatment. Okay, so for instance, that's a modeling framework that's very well suited to randomized control trials, because in the randomized control trials, we effectively randomly assign some units to the treatment, some units to the control. So treatments are random. Okay. Then we can take a model-based perspective where it's the opposite. In that perspective, we're going to assume that the treatments, the study design is non-stochastic. That thing is fixed. And what's random are the potential outcomes. So for instance, we assume that there are stochastic shocks that affects a group's potential outcomes. So for instance, if you're interested in the effect of an intervention on agricultural yield, you could assume that the yield in the village G in year T depends on the weather in that village on that year, and the village has an element of randomness into it. And so that's what makes the potential outcomes random. So then the third approach is the sampling-based perspective, where the randomness comes from the fact that we assume that the G groups we observe are a random sample from a larger population. So under that perspective, each time you draw a new random sample of groups, you're randomly drawing their potential outcomes and their treatments. And therefore, under that perspective, both the potential outcomes and the study design are going to be random. So the design-based and the sampling-based perspectives have gained a lot of traction recently, because an appeal of these procedures is that when the researcher effectively randomizes who is treated, who isn't treated, or when the researcher effectively randomly draws its sample from a larger population, then you can conduct inferential procedures that are going to be uncontroversial, in the sense that you're going to be able to compute the variance of your estimators with respect to the randomization of units to treatment and control that you effectively conducted. So you're going to be able to compute the true variance of your estimate. Similarly, you're going to be able to compute the true variance of your estimator with respect to the sampling you conducted to create your sample. From that perspective, the model-based perspective might appear to be less appealing because that one always needs to rely on a thought experiment where you need to imagine that nature drew some shocks that affected your potential outcomes, but then to compute the variance of your estimators, to construct confidence intervals, etc., you're going to need to make an assumption, a judgment call on how nature drew these shocks, and in particular on whether the shocks are correlated. And of course, as researchers, we prefer uncontroversial inferential procedures to procedures that involve us making judgment calls on critical assumptions in our model. Now, given that the focus of this book is on natural experiments and not on randomized experiments, in natural experiments, researchers do not effectively randomize treatment. So if they want to invoke the design-based perspective to guide how they're going to compute the variance of their estimators, how they're going to construct confidence intervals, etc., they are also going to need to make a thought experiment where they're going to need to imagine that someone randomly assigned the treatment, and they will need to make assumptions on whether it is more likely, say, that this random assignment was made independently across space, or independently across time periods, or independently across both dimensions, or across none of those dimensions. But so the point here is to say that in the context of a natural experiment, the design-based perspective is going to involve the exact same judgment calls that the researcher has to make as the model-based perspective. And so it's not the fact that the design-based perspective is kind of assumption-free is no longer an advantage of this way of conducting inference in the context of natural experiment. And the same applies to the sampling-based one, because in most of the Diff-in-diff studies that we're going to revisit, researchers are not using a random sample from a larger population in their analysis. Actually, in many cases, they are using the full population. They are using all the municipalities of a country or all the regions in a country. And then the sampling-based perspective is also going to involve a judgment call, a thought experiment, where the researcher has to imagine that their sample of the 50 US states or of the 27 member states of the European Union is actually a random sample drawn from an infinite population of US states or an infinite population of member states of the European Union. Okay? So the bottom line, in some sense, it's not necessarily good news, but the bottom line is that when you analyze natural experiments conducted in the full population, conducting statistical inference is always going to require making thought experiments, making judgment calls, irrespective of whether you place yourself in the model-based, in the design-based, or in the sampling-based perspective. So, of these three approaches, we are going to adopt the model-based one. Okay? Why is that? Well, there is one approach that we are going to clearly discard, which is going to be the design-based perspective. The reason is that this approach assumes that the treatment is randomly assigned, or that at least the timing at which units get treated, or those that get treated first, earlier or later, that's randomly assigned. And this type of as good as randomly assigned assumptions, have many testable implications. For instance, they imply that the baseline outcome levels should be the same for the early and for the late treated, for instance. And we're going to show that in most of the empirical applications we're going to revisit, these testable implications are clearly violated. So we're not going to adopt this design-based perspective because it seems to be unrealistic in many natural experiments. So essentially, random assignment is not something that happens randomly. Okay? So unless a researcher randomly assigns some units to the treatment of the control, if instead the researcher does not have the control over the assignment to the treatment, then it's pretty unlikely that this assignment took place as good as random. So then are two options left. The model-based or the sampling-based one are not very different. And we're going to favor the model-based one for pedagogical reasons. Essentially, in the model-based one, the design is going to be conditioned upon. We're going to treat all the treatments as non-stochastic deterministic quantities. And that's going to make it very easy to compute, to derive the finite sample properties of many of our estimators. We're going to be able to compute the expectation of our estimators, the variance of our estimators. And therefore, when we're going to try to compare estimators, in many cases, we're going to be able to do these comparisons mostly only using the finite sample properties of our estimators, whether they're unbiased or not. And if two competing estimators are unbiased, then we can just try to see which of the two estimators has the lowest variance. And while in more complicated econometrics models, when you cannot derive the finite sample bias and variance of an estimator, then you need to resort to lab sample asymptotics to discriminate between estimators. And in most cases, we will not need to do that, which is a pedagogical advantage. So because we adopt the design-based approach, the design big D is going to be conditioned upon in most of this book, but do not make the notation too heavy. We are going to leave the conditioning implicit. So whenever you see an expectation of X symbol, you should actually understand it as an expectation of X conditional on the design. The fact that the conditioning is being left implicit has no implication for all the results we derive that concerning the expectation of the estimators we consider, because if an estimator is conditionally unbiased for a target parameter θ0 that might depend on the design big T, then by the law of iterated expectations, θ hat is going to be unbiased for the expectation of this design-dependent parameter θ0 of okay. The fact that we condition on the design will have a bit more implications for the variance estimators we consider. We are going to be considering variance estimators that are going to be unbiased for estimators of conditional variance given the design. And the conditional variance of an estimator by the law of total variance is not the same thing as its unconditional variance. Actually, it's lower than its unconditional variance. But that does not mean that our variance estimators are invalid. They are valid measure of the variability of our estimators, but just they do not account for the variability in the estimators that would arise if we were to modify the design by, let's say, instead of having 30 treated groups and 20 control groups, we had 34 treated and 16 control groups. This type of this could lead to changes in our estimator data, and this extra variability is not going to be accounted for. So then those shocks, those common shocks are not necessarily ruled out by the independence assumption, but they might just be implicitly conditioned upon. And what we assume is that group's potential outcomes are assumed to be independent, conditional on common shocks. So to make this a little bit more concrete, let's consider an example where we have US county level panel data. Okay, so G represents a county in the US. Then we could assume that a county's outcome evolution without treatment can be decomposed into a stochastic shock M SG of T that's common to all the states that county G belongs to, plus another stochastic shock small mgt, that's the micro shock that's specific to county G, while big M is the macro shock that's common to all the counties in the same state. Now, under that assumption, we could have that potential outcomes are independent across counties if we actually make this independence assumption here conditional on the macro shocks, because then conditional on those shocks, the only stochastic part in the potential outcomes are just the micro shocks, and those could be independent across counties. Now, if we make this assumption conditional on the macro shocks, our parallel trends assumption also needs to hold conditional on the macro shocks. Okay, and this parallel trend assumption can hold. So the one we made here, the strong parallel trend assumption we made here cannot hold conditional on the macro shocks, because then if you, given the model I had earlier where this can be decomposed into a macro and a micro shock, well, conditional on the macro shock, the expectation of this is equal to the macro shock, and the macro shock is not constant across G, so you will have a violation of this assumption. But as I said earlier, actually, for our results to hold, we can have a weaker version of the assumption where we need to have parallel trends on average across the treated and the control groups. And now this weaker parallel trend assumption can hold conditional on the macro shocks if the average of the macro shocks are the same for the treated and for the control counties. Okay. So it's just to say that this independence assumption does not necessarily rule out common shocks affecting several counties. The analysis then has to be conditional on those common shocks, and the parallel trend assumption needs to be conditional on those common shocks, meaning that the common shocks do not lead to a violation of the parallel trend assumption. And so that leads us, that's very related to the next question, which is the complicated issue of the level at which one should cluster standard errors. Yeah? In other words, at what level should we make this independence assumption here? So, following the very influential work of Bertrand and others, the common practice has been to make the independence assumption at the level at which the treatment is assigned. Okay, and then you cluster standard errors at that level. So, for instance, if your data is at the county level, but you have if the data is at the county level, but you have a treatment that's assigned at the state level, then the recommendation from the Bertrand paper would be to cluster standard errors at the state level. So this approach is clearly uncontroversial in a design-based approach to inference. So if you have a treatment that's randomly assigned at the state level, but your data is at the county level, then you need to cluster your standard errors at the state level. Now, in the model-based approach that we adopt, this recommendation of clustering at the level at which the treatment is assigned might not be the only possibility. And instead, it's not necessarily a necessarily crazy idea to cluster in that example at the county level. The main motivation for clustering at that level is that clustering at the state level might lead to very non-trivial power losses. And there's been a recent literature that has highlighted the fact that power is often a very first-order concern when we analyze natural experiments. Now, of course, if we have state-level shocks that are not netted out when we cluster at the county level, those state-level shocks, they could lead to differential average trends across the treated and control counties. You could have that the average state-level shocks for the treated counties is not the same as the average of the state-level shocks for the control counties, which would lead to a violation of your parallel trend assumption. But to assess if that's a concern, then we're going to have three trends tests. And the role of those tests will be exactly to detect if prior to treatment, there seemed to have been, shocks affecting the treated and the control counties that led to different trends. And if that's the case, if those pre-trend tests are showing differential trends, then the analyst will try to adjust the model, for instance, by controlling for some covariates until they seem to have managed to, quote-unquote, kill the pre-trend. If instead you cluster your standard errors at the state level, that's going to very slightly change the parallel trend assumption that you will need to make without necessarily weakening that parallel trend assumption. But another consequence is that will decrease the precision of all your estimators, including the estimators of the pre-trends, which could lead you to fail to detect pre-trends and adjust the model. So the bottom line is that due to the panel structure of the data, some clustering is necessary. Okay, it makes sense that because you're going to observe the same G across several time periods, you want to allow for time series correlation between for the repeated outcome measurements of the same unit over time. So you need to cluster at one level. Then, when deciding the level at which to cluster, I think there are two possibilities. Either you follow the Bertrand recommendation and you cluster at the level at which the treatment is assigned, which is what the vast majority of applied researchers are doing at the moment. Or you follow the arguments that we outlined in this book, which are to say that in a design-based perspective, there is not really a strong argument to cluster at the level at which the treatment is assigned, and that to maximize power, both to estimate treatment effects, but also to potentially reject your parallel trend assumption and use a more sophisticated model, you might want to cluster at a more disaggregated level. Okay, and finally, the final point in this introductory chapter is the fact that even though in most of the book we're going to use the model-based perspective for inference, we will sometimes adopt the sampling-based one. And so sometimes we're going to assume that the G groups we observe are an independent and identically distributed sample. And we're going to make that assumption when it really simplifies a lot the exposition. And so at the end of the course, we're going to start talking about treatments that could be potentially continuously distributed variables, where you don't have any two groups in the population that have the same value of the treatment, because the treatment is a fully continuously distributed variable. Then to help us think about the continuous distribution of the treatment, it's going to be useful to introduce an infinite superpopulation of groups, because in a finite population, you cannot define something like a continuous distribution. Okay? So the fact that we are going to go back and forth a little bit between these two conceptual frameworks, the model-based one and the sampling-based one, is going to impose a little bit of a cognitive cost on you. At the same time, it's not a bad idea to learn how to speak those two different conceptual languages, because in the methodological literature of Diff-in-diff, some papers use the model-based approach, others use the sampling-based approach. So being able to go back and forth can be helpful. And so when we adopt the sampling-based perspective, we are going to replace our independence assumption by a slightly stronger assumption, where we assume that the potential outcomes and the treatments of all groups are independent and identically distributed, instead of just assuming independence. And so because we assume that we have identically distributed groups, then we'll be able to also drop the G subscript. And in the sampling-based perspective, it's not only the potential outcomes that are random, also the treatments are random. And therefore, when we write expectation of something, it's no longer just an expectation with respect to the potential outcomes and conditional on the treatment. It's an expectation. It's an expectation with respect to both the potential outcomes and the treatments. And so we denote expectations like that, which are not conditional on the design. We will denote them by E subscript U to highlight the fact that those are unconditional expectations. And so as a first translation exercise of going back and forth into the two conceptual framework, in the model-based framework, we write the parallel trend assumption as follows. We say that the expected average outcome evolution without treatment is the same for the treated and for the control group. In the sampling-based framework, the exact same statement can be written as follows. We say that the conditional expectation of the outcome evolution among the treated groups is the same as the conditional expectation among the control groups. Okay? And that way of formulating the parallel trend assumption might be a way that some of you have already seen in the literature. For instance, if you look at the seminar papers by Abadi, that's the way you write down the parallel trends. So I'm thinking maybe before we start the next chapter, maybe now is a good time to do a first Q&A. So should I look at the message that Andrea you just sent in the
Yes, we have two main questions there.
Yeah. Interesting. So then in cases where, so the question is that even in the natural experiment, you might still have some random sampling. And more generally, you might have a mix of randomness on the treatment, on the outcome, etc., etc. So if you want to incorporate this type of additional uncertainty, then the most general approach is to actually use the sampling-based one, because the sampling-based approach will incorporate uncertainty on potential outcomes that could come from shock, but also uncertainty on the treatments that could come from sampling or from random assignment to the treatment. And so the variance estimators that we're going to see do not incorporate that variability. They are really conditional on the design and the sampling, etc. In principle, so typically that means that the variance estimators we're going to see might be a bit downward biased with respect to what they should be if we were to also incorporate that additional source of variation. In practice, I don't think it typically makes a very large difference. Okay, and then there was a question, clustering when units are not nested. So the counties where immigrants live may not be nested with the treatment unit. Do we still cluster? Okay, yeah. So yeah, I would tend to think that in that case, so I think there are two distinct issues. So one question, so with this, like, country of destination and county of destination, county of birth, county of residence, county of birth, there is a bit of concern also that you could have selective migration determined by the treatment. So then people try to stick to county of birth to cancel out that possibility, to control that possibility. But that's more like a concern with identification, not necessarily with inference. Then I think in a design-based perspective, you would want to cluster at the level at which the treatment is assigned, namely here a county of birth. But in the model-based perspective, where you would want to cluster at the level at which the outcomes are determined, which here would be county of residence, so that could indeed be a way to justify two-way clustering in this type of settings. If you want to have standard error estimators that account both for the variation in the design and the variation in the outcome, that would indeed motivate two-way clustering. Okay, good. So now let's start with our study of classical Diff-in-diff designs. So the classical Diff-in-diff design is going to be a design where we have a treatment that's absorbing that's binary. So we have a 0-1 treatment. Then the treatment is absorbing, meaning that once a group is treated, they cannot go back to being untreated. You cannot switch out. And there is also no variation in treatment time. So mathematically, we can express this type of simple design by saying that DGT is an interaction between T being greater than date F, which represents the first date at which the treated groups are treated, and an indicator DG that's equal to 1 for the groups that belong to the treatment group and to 0 for the groups that belong to the control. So now we're going in this type of designs, we're going to let G1 denote the number of treatment groups, and G0 is going to denote the number of control groups. T1 is going to denote the number of treatment periods, and T0 is going to be the number of control periods. And finally, N1, which is the product of G1 times T1, that is going to denote the number of treated GT cells. So
sorry to interrupt you. Can you click on a mask on hiding?
Yeah.
Can see the box. Thank you.
Yeah. So the running example for the data that you're actually going to use to illustrate this chapter is actually coming from the following natural experiment. So during World War I, the US passed the Trading with the Enemy Act, whereas a punishing measure against German firms, they decided to systematically license to US firms patents that were owned by German companies. Okay? And at that time, that was a point in time where Germany was really like the world leader, especially for organic chemical industry. And the mother and brother used that as a natural experiment to study the effect of getting access to new patents, to new knowledge that for free that you used to have to pay for before, on domestic innovation in the US. And so the data that they use is a balanced pattern which is at the organic chemistry subclass level, where they have like more than 7,000 subclasses. And for each year from 1900 to 1939, they have the number of patents in each subclass and in each year. And so the treatment DG is an indicator for the 336 subclasses that received at least one German patent under this reform. And then DGT satisfies the equation we just saw earlier. It's equal to an indicator for T being larger than 1919, the year when the TWA took place, and being part of the treatment. And so you got access to this data set, which we're going to use to answer some of the green questions, in this chapter. And the book contains the following variables. So you have a G identifier for the subclasses, a T identifier for the years, a treatment group indicator for the 336 treated subclasses, post for years after 1990. TWA is the treatment indicator. And then we have all these relative time indicators. So those dummies are equal to 1 for GT cells such that G is a treated subclass, and T is such that the treatment has been in effect for 1 year. That one is equal to 1 for GT cells, such that G is a treated group and the treatment has been in effect for 2 years, etc., etc. And then you have similar relative time indicators, but for years before the treatment. So for instance, this one is going to be equal to 1 for treated subclasses, and 1 year before they get access to treatment, etc., etc. Patents is going to be the outcome. This one is going to be the change in the number of patents in subclass G from 1918, the year just before the reform, to the FT. And finally, we have this one here, which is the number of patents in 1900 in subclass G. So the baseline number of patents in subclass G, which we'll only use in the next chapter. Okay, so now let's define the target parameters we're going to try to learn in this chapter. So first, the most disaggregated treatment effects we can define are going to be effect at the cell level, at the GT level. And so TGT will be for any cell GT that's treated, meaning that G is a treatment group and T is after F. We're going to let TGT be the expectation of the difference between the actual outcome of group G at time T minus its counterfactual without treatment. And so at period T, if G is the treated group and T is after F, then we know that the observed outcome of cell GT is actually its counterfactual outcome under F-1 period without treatment, and T minus F-1, so T minus F+1 periods of treatment, where bold one of T denotes a vector with T1. Okay, so we are comparing what happens to that cell after T minus F+1 years of exposure to treatment versus having never been exposed to the treatment. So now the issue with this type of effects is that they apply to only one GT cell. So we're never going to be able to consistently estimate such disaggregated effects. In the Moser and Buena example, we cannot estimate a treatment effect specifically for a given subclass. Okay, we are only going to be able to consistently estimate average treatment effects, more aggregated effects. And so the first commonly studied aggregated effect is the ATT, where we just average all of the TGTs across all the treated sets. So if we rule out dynamic effects, then the ATT reduces to that expression here, which is just a standard average treatment effect on the treatment. Now, we might also be interested in disaggregating the ATT a little bit more. So the ATT TGT is the most disaggregated effect you can think of. ATT is the most aggregated effect you can think of. Now, we can go somewhere a little bit in the middle by considering these ATTL effects, where we average across all the treated groups their effects at date F-1 plus M, namely L periods after the treatment has started, which are effects of having been exposed to the treatment for L periods rather than unexposed. So one gets shown that actually the ATT is just a simple average of the ATTL. So the ATT is an average of the effect of being exposed to treatment for 1 year, the effect of being exposed to treatment for 2 years, etc., etc. Now, the caveat that there is in the interpretation of ATTL is as follows. So, if we find that for two different values, N and L prime, ATTL is different from ATTL prime, that difference is not completely straightforward to interpret, because it could be due to the fact that ATTL and ATTL prime are effects of different lengths of exposure to the treatment. But it could also be due to the fact that those effects are measured at different points in time. So, for instance, if you find that ATT2 is strictly larger than ATT1, can you conclude that 2 periods of exposure to treatment have a larger effect than just 1 period of exposure?
We have one answer that says no.
So, yes, we cannot necessarily conclude that. And that's because ATT2 is an average effect of having been exposed to the treatment for 2 periods that's measured at date F+1, while ATT1 is an average effect of having been exposed to the treatment for only 1 period, but measured at date F. So if you are ready to assume that treatment effects do not vary with calendar time, that effects of 2 periods of exposure are the same at date F+1, at date F, at any date, then indeed you can interpret ATT2 larger than ATT1 as evidence that being treated for 2 periods has more of an effect than being treated for only 1 period. But if you're not ready to make that assumption that there is no calendar time effect, then it could be that ATT2 could be greater than ATT1, not because 2 periods of exposure has more of an effect than 1 period of exposure, but just because 1 period of exposure has a larger effect at date F plus 1 than at date F. Okay, so that's the difficulty that we have in interpreting this type of ATTL event effect that we're going to call event study effects. And of course, economically, we would want to know whether treating people for 2 periods is more effective than treating them for only 1 year, especially if treating people as the cost that has to be paid at each period of exposure, then you would want to know what is the optimal number of periods for which you should treat individuals so as to maximize the effect at the lowest possible cost. But unfortunately, the type of event study effects that we are going to study cannot allow us to answer this type of economically interesting questions unless we are willing to rule out calendar time effects. Okay, so now that we have some target parameters, let's start by introducing some estimators of those targets. And so, because we saw that there is this one-to-one mapping between the parallel trend assumption, which we assume, and having a two-way fixed effect model for the untreated outcome, it seems natural to see if under parallel trends, maybe we can estimate treatment effects using a two-way fixed effects regression. So beta at F is going to denote the coefficient on DGT, the treatment in group variety in an OLS regression of YGT on group fixed effects, period fixed effects, and DGT. So YGT is regressed on dummies for every group, dummies for every time period, and the treatment DG. And we're going to refer to beta at FE as the TWFE estimate, two-way fixed effects. So the first green question for you that I would like you to try to answer using the data set of Causal and Buena is to run the two-way fixed effects regression of the number of patterns in subclass G and EFT on subclass and EF fixed effects and the treatment, clustering standard errors at the subclass level. So you may either use the XT reg or the reg HDFE current. And according to this regression, do we have that compulsory licensing as an effect on US innovation? I'm giving you a bit of time to run the regression. No worries. Okay, so was someone able to run the regression? You find a positive, a negative effect on innovation? No effect?
We still don't have any answer.
Okay, so let me run it then. So I'm uploading the data. And I'm going to use only one of the two methods, the one with reg HDFE. And I'm running the regression of patterns on the treatment, absorbing the subclass and EF fixed effects. And doing so, I'm finding a very, very positive treatment coefficient, which is highly significant. And in relative terms, so this, we can interpret it as the average outcome that would have prevailed in those subclasses without treatment. And you see that the treatment leads to a very strong increase in the number of patterns that represents, in relative terms, more than 2/3 of the baseline level. Okay, so that would suggest a very large effect of this compulsory licensing on patent. That having access to these German patents fostered innovation in the goods. So in the simple designs that we are considering for now, there is it turns out that the beta at FE actually reduces to a very simple Diff-in-diff. And to see that, we can first show that actually the coefficient on the treatment variable in this regression here would remain exactly the same if instead of having fixed effects for all the groups and fixed effects for all the time periods, we replaced the fixed effects for all the group by just an indicator of the treated groups. And then we replaced the fixed effects for all the time periods just by an indicator for all the time periods after the treated groups start receiving the treatment. Okay, and then because this regression is a simple saturated regression, we could then show that in this simpler regression, beta at FE is a simple Diff-in-diff that's comparing the average outcome across all the treated GT cells, namely those in the treatment group and at time periods after the treatment. And then we subtract from that the baseline outcome in the treated group before the treatment. And we compute the same evolution from the average outcome from before to after the treatment, but in the control group. Yeah, and that's finally how we get our DID Diff-in-diff estimation. So here, we're not going to go to do it together, but here there is a formal proof that beta at FE has this expression here. But now we are going to verify, rather than proving the result, we're going to verify that it works in an example in this application. We're going to verify that beta at FE is indeed equal to the coefficient on the TWEA treatment in a regression of patterns on the treatment group indicator, the post-treatment indicator, and the TWEA treatment. So here I run the much simpler regression. And when I do that, you see that the coefficient on the TWEA treatment from the regression with all the group and time fixed effects is exactly the same as the coefficient in the much simpler regression. The standard errors are almost the same. They are very slightly different, but that's only due to the the degrees of freedom adjustment automatically applied by Stata and by most standard statistical software, due to the fact that this regression has much fewer variables and therefore less degrees of freedom adjustment than this one. Okay, and so that, quote unquote, proves the first equivalence that I get, saying that beta at FE is equal to the coefficient in the simpler regression. And then you could also verify in this example by computing this Diff-in-diff by hand, by computing the 4 averages and taking then their Diff-in-diff, you could verify that this coefficient, this regression is indeed the simple and Diff-in-diff, but I will leave this for you as an example. So now we're going to show that beta at Fi is indeed a good estimator of the ATT in the sense that it's unbiased for the ATT in the classical design with a binary absorbing treatment without variation in treatment timing, and under the no anticipation and parallel trend assumption. So we're going to prove this result. And so the proof goes as follows. So we start by saying that we can rewrite the observed outcome YGT, the expected observed outcome, as the expectation of the never treated outcome plus the treatment times the expectation of the difference between the observed and the never treated outcome. So what's the justification for this first equality here? Okay, so this type of equality is a type of, foundational, definitional equality in causal inference that relate an observed outcome to potential outcomes and the effect of the treatment. So the first one we're seeing in this class, we're going to see many of them, so it's worth it spending a little bit of time to really explain what those type of equalities. So to verify that this equality is true, we are going to verify that it holds for all the values that DGT can take. Okay. So we're going to fix DGT at the first value it can take and show that the equality holds, and then fix DGT as the second value it can take and show that the equality holds, etc. Then, if it holds for any value of DGT, then the equality has to be true. So here it's not very complicated because DGT at this stage can take only two values, 0 or 1. Okay. So if DGT is equal to 0, then the right-hand side of this equation reduces to that term here. Okay, so then what we need to show is that E of YGT is equal to E of YGT of ball 0t whenever DGT is equal to 0. And that equality is true because if DGT is equal to 0, that means that G is not treated at period t because DGT is equal to 0. And in the designs we consider for now, if a group is not treated at t, that means that this group has never been treated in the past as well, such that its observed outcome YGT is actually its never treated outcome. Okay, so therefore the left-hand side is also YGT of ball 0t. So the equality holds for DGT is equal to 0. Now let's show that it also holds for the second possible value that DGT can take, which is 1. If DGT is equal to 1, the right-hand side of the equality is this term. So this is 1 plus this term minus that same term that we had here. So the two terms cancel. And so we only get E of YGT. And so the equality just says that E of YGT is equal to E of YGT, which is tautologically true. Okay. So we verified that this equality holds for any possible value of DGT. So it has to be true. Then the second one here is just by definition, we have actually defined DGT as being equal to this quantity. Okay, so now let's compute the expectation of beta at Fi. So we're going to start from this equation for beta at Fi. Okay, so we know that beta DFI has this expression here. Then we have that E of beta DFI is E of this whole thing here. And then using the fact that the design is conditioned upon such that this thing is not random, none of those things is random, etc., etc. And the linearity of the expectation operator, we can rewrite E of beta DFI as the average of the expected outcome of the treated cells minus the average of the expected outcome of the treatment groups prior to treatment, etc., etc. Then, once we are at this stage, we are going to plug in this decomposition of YGT into this expression. And in these three summations here, treatment group before treatment, control group after treatment, control group before treatment, we know that actually the DGTs are all equal to 0, such that this actually reduces to just that expression here. Okay, so when we plug, we are actually only plugging this down. There is only for that first summation here, for the treatment group after treatment, that we have the untreated outcome plus the treatment. Now, to go from here to here, we are going to split this summation into 2. So we're going to have 1 over G1 T1 summation of the TGTs times DGT across all the treated cells, but DGT is just a 1 for those cells. So we have just the average of the TGTs, which we've defined as the average treatment effect on the treatment. Okay. Then we're left, so then we have ATT plus some kind of diffs-in-diffs of the expected outcomes without treatment in the treatment group after treatment, treatment group before treatment, etc., etc. Now, how do we go then from these diffs-in-diffs on the Y0s to this expression here, where we have the group fixed effects and the period fixed effects? So that's good. So going from here to here, beyond the step to get the ATT that we've already discussed, comes from the fact that under the parallel trend assumption, we have that the untreated outcome, the mean and the expected untreated outcome actually follows a two-way model, can be decomposed into a group fixed effect alpha G and a period fixed effect gamma T. So that's what we're using to go from here to here. So finally, the last step says that this is ATT, and so that must mean that this is 0. And this is indeed 0 because the average of the alpha G's, so you see here we have 4 summations. It turns out that the average of the alpha G in this summation cancels out with the average of the alpha G's in one of these other 3 summations. Does the average of the alpha G in this first summation cancels out with the average of the alpha G's in the second, or in the third, or in the fourth summation? So maybe you can answer via the chat. Yeah, exactly. The average alpha G for this summation, which is the average alpha G for the control groups, cancel out with the average alpha G for the control groups in this summation. So the alpha G's are gone. Now for the gamma T in this summation are for the time period after treatment. So they cancel out with the gamma T's in this summation, which are also for the time period after treatment. And similarly, the gamma T's in this summation here, which are for time periods prior to treatment, cancel out with the gamma T's in this summation. Yeah, so I was saying that that for the gamma T's, the average, so in this summation, we have an average of gamma T's in the post-treatment period, which is going to cancel with the average gamma T's in this summation, which is also for the post-treatment period. And in this one here, we have an average of gamma T's for the pre-treatment period, which is going to cancel with the average gamma T's in this summation here. Yeah. Okay, so we're going to skip this less essential part. And so, Andrea, what do you think we should do? Because we are a bit over time. At the same time, we started a bit late. On my end, I can continue for a few minutes, but maybe make people have to leave. So what do you think is best? Should I continue for like a few minutes or?
I think you can continue. And then you stop when you want. I can see we're at 1 hour and 42 minutes now, but you stop when you want.
Yeah, okay. So I can keep going for at least 10 minutes. So I'll stop at around the quarter to 5. Okay, let's do that.
Thanks.
Okay, so now researchers analyzing classical Diff-in-diff designs, they often do not stop at the static two-way fixed effects regression we've just discussed. Oftentimes, they also estimate what we're going to call an event study two-way fixed effects regression, or TWFEES, two-way fixed effect event study regression. So that's a regression of the outcome of G at T on an intercept, a dummy for the treatment group. Fixed effects for every time period, except, of course, we need to have a reference time period, except for the time period just before treatment, which is going to be our reference time period. And then instead of just having one, the DGT indicator for all the treated cells, instead we're going to have these relative time indicators. So we have indicators for period T being F-1 plus L, namely L periods away from the start of the treatment, where L is going to range from negative values to positive values. So L is going to go from minus F plus 2 to T minus F plus 1. So namely indicators for time period before or after treatment expressed in relative time to the start of the treatment, interacted with the treatment group. So the regression, if you count, this regression has exactly 2 times T explanatory variables, which is the number of values that the vector of its explanatory variables, which are essentially the treatment group dummy and the time dummies, because here time is expressed in relative terms, but your relative and absolute times are going up to each other. So the explanatory variables take also 2 T values. And then because we have a linear regression with as many explanatory variables as the number of values that the explanatory variables can take, that's a regression that's saturated. And here I refer you to this section of the Bosnia-Arnes Econometrics textbook for a refresher, if needed, on saturated regressions and their properties. One nice thing about saturated regressions is that the predicted values from the saturated regression are just the conditional mean function of YGT given the explanatory variables. And all of the coefficients from the saturated regression can be expressed as simple functions of that conditional mean function. And so in particular, we're going to be particularly interested in the coefficients on the relative time indicators. It's possible to show that beta at FEL has this simple expression here. It's just a simple Diff-in-diff comparing the F-1 to F-1 plus L outcome evolution of the treated groups and the control. Here, that's where the fact that F-1 is our reference period, that's the baseline with respect to which outcome evolutions are being computed. And what you can also see is that when L is positive, those Diff-in-diffs are Diff-in-diffs going from the past, F-1, to the future, F-1 plus F. But when L is, let's say, -1, we are actually doing a Diff-in-diffs that going from the future, F-1, into the past, F-2. Okay. So those event study regressions, they can serve two purposes. The first one is to estimate those more disaggregated treatment effect parameters we've discussed earlier. So we've seen how to estimate the most aggregated one, the ATT. But we said that we could potentially be interested in more disaggregated effects, the ATTL effects by length of exposure. And here you see that for the positive values of L, for instance, beta FE1 is unbiased for the effect of being treated for one period. Beta FE2 is unbiased for the effect, for the average effect of being treated for 2 periods, etc., etc. And that's true under the non-anticipation and parallel trends assumption. So the proof of that result goes as follows. So we start, we have that our beta TPL coefficient is the simple Diff-in-diff I just described. So its expectation is the expectation of the Diff-in-diff. Then we use the fact that treatment groups at date F-1 are untreated, so their observed outcome is their never treated outcome at that date. Same thing, the control groups are never treated, so at both F-1 plus L and F-1, what we observe is their never treated outcome. And act for the treated groups at F-1 plus L, where those groups have been treated since they happened. So at F-1 plus L, they've been treated for L periods. So the potential outcome that we observe for them is a potential outcome with F-1 period without treatment and L period of treatment. Okay? So now, can someone explain to me how we go from here to here?
Yeah, exactly. So that's what my students often call the magical zero trick, when you add and subtract the same thing. And I'm insisting on it because that's essentially the same trick that we're going to use again and again in all Diff-in-diffs identification proofs. We just add and subtract the potential outcome without treatment of the treated groups at date F-1 plus L. Here I'm subtracting it, and here I'm adding it. Okay. Now, this term is a treatment effect. Here we're comparing the same groups G at the same period F-1 plus L under two counterfactual states of the world. The counterfactual state of the world where those cells are untreated for F-1 period and then treated for L periods versus never treated for F-1 plus L period. So that's a treatment effect of being exposed to treatment for L period. And the average of those effects for across all the treated groups is what we've called ATTL. Now, why is it that this is equal to 0? By which assumption? Yeah, actually, Beatrix has already answered to that question. That's by the parallel trends assumption. Yeah, exactly. Okay, by the parallel trend assumption, this is equal to 0. And here I want to highlight that all the results, so here it's very apparent from this proof here. This proof is, to prove this result, it's enough to assume the average parallel trend assumption between the treated and the control instead of all groups are experiencing parallel trend assumption. That was a little bit less obvious in the proof of theorem 1. The way I proved this result there, I used the two-way model, which then implies that every groups are on parallel trends, but actually theorem 1 as well could also be proven by only using the average parallel trends assumption. Okay, so I'm going to stop here for today. Maybe I don't know if there were like questions that I did not see on the chat for this chapter 3 that we could discuss now.
Yes, there were 2 questions. I can write in the comment chat again. So at the beginning, we had an assumption of non-dynamic effects. And at that time, there was this question about that.
So the no dynamic effects assumption will not be crucial. It's only going to become really important at the very end of the class. In the first chapters, we are sometimes going to make that assumption, but it will just be out of notational convenience to alleviate the notation a little bit. You can see already that potential outcome notation with dynamic effects are a bit cumbersome because potential outcomes depend on many arguments. So sometimes just to simplify notation, we will rule out dynamic effects, but that will not be of essence, or that we are going to say would still apply with dynamic effects. It's going to be at the very end of the class that sometimes we will rule out dynamic effects, and to simplify not notation, but to simplify the analysis at the expense of the estimators that we will be able to propose, at the expense, of course, that those estimators could be invalid if in reality there are dynamic effects. Okay. But at this stage, it's not, we don't restrict dynamic effects at all.
The second question, I think, came when we spoke about clustering.
Is assuming that the concern of correlation across groups allowing for serial is much more harmful than say. So all the very good question. All the standard errors we're going to be using are going to be robust to heteroscedasticity, of course. So in practice, I don't, whether assuming wrongly homoscedasticity would be more harmful or less harmful than wrongly assuming independence, while in reality you have serial correlation. I don't think there is like an answer to that question that will always be true. Intuitively, I would say that neglecting serial correlation is probably more of a concern than neglecting heteroscedasticity in many realistic scenarios. But you could probably come up with examples where actually it's more important to account for heteroscedasticity. So there is probably not like a ground rule here. Okay, perfect. So thanks everyone, and so I'll see you then on Friday, and have a good rest of the week till then.